Okay, greetings everyone. My name is Chen Li, and I'm a PhD candidate from the University of Alberta. And I'm glad here today to present our work, One for All for One, Learning and Transferring User Embeddings for Cross-Domain Recommendation. And this work was done, sorry. Okay, oh, thanks. And this work was done when I was doing my intern at PCG in Tencent. And Okay, let me first introduce some background. And as we know, that data sparsity has been a persistent problem in recommendation systems. And to handle this, the cross-domain recommendation tries to transfer knowledge or data from one domain to another to improve performance in sparse domains. And different from the traditional cross-domain recommendation scenario, where the methods all trying to model the relationships between two domains, the multi-target cross-domain recommendation, or MTCDR, goes a step further by simultaneously enhancing the performance in 3 or more domains. And the MTCDR has gained popularity recently, and we have summarized the 3 shared features by all the previous solutions. To begin with, they're all trying to study or extract a shared global user representation to achieve knowledge sharing across multiple domains. And secondly, this global user representation is often jointly trained by all domains through specific models such as graph neural network in hero graph or the probabilistic matrix factorization in MPF. And finally, they all require that all the participant domain to share their raw user interaction data and also train their recommendation models simultaneously in all the domains in order for the global representation to be effective. And although those approaches have achieved some progress, there are still some unsolved issues or challenges that hinder the development of MTCDR solutions. For example, they all fail to take the lecture transfer problem into account. And the lecture transfer refers to the problem when the transferred knowledge or data may negatively affect the performance in the target domain due to irrelevant or noisy information transferred from the source domains. And furthermore, their training of the global user embedding is based on the raw data collected from all the domains, which may also be problematic in some cases. To start with, we know that there might be a great disparity in the amount of data collected from different domains, and therefore the training samples for the global representation may be unbalanced from the different domains, and this will result in the global representation be biased towards domains with a larger number of training samples, as demonstrated in the figure on the right. And furthermore, this biased global representation, when transferred to a specific target domain for recommendation, it may introduce noise and cause negative transfer. And finally, sharing the user's raw interaction data may also contravene certain privacy protocols in some domains. Okay, to handle those challenges, in this work, we propose a straightforward yet very effective method. To begin with, we pre-train the recommendation models in individual domain and then just share the user's latent representation among multiple domains to avoid direct sharing of users' raw data. And we also figured out there may be 2 types of user embeddings that can both be beneficial for MTCDR. The first is the unbiased global user representation, which will capture the user's domain invariant characteristics. And the second is the domain-specific user embeddings, which will model the user's behavior pattern or preferences in various domains. And to leverage both user embeddings for MTCDR, we set up 2 learning objectives. That is the one for all objective, in which we were focusing on extracting the one unbiased global user representation for each user based on their pre-trained user embedding in all the domains. And this unbiased representation can then be transferred to all the target domain for negative transfer-free recommendation. And in the all-for-one objective, we will transfer all the useful features or representations from all the domains to a specific target domain for enhanced recommendation, as demonstrated in the figures on the right. And specifically, for achieving the one-for-all objective, we first built an autoencoder which takes the pre-trained user embeddings from all the domains as input, as shown in the figure. And through a reconstruction task, the extracted global user representation is supposed to contain the most important information from all domains. However, this input of the autoencoder, which is a pre-trained user embedding, is highly likely to be affected by the data quality or sparsity issue in each domain. And therefore, low quality or under-trained user embeddings from a sparse domain may introduce noise into the input of the autoencoder, and consequently cause the global user representation to be biased towards dense domains. Therefore, to handle those and also to extract a more general and noisy robust global user representation, we first incorporated the contrastive learning paradigm into the autoencoder framework, and that is our contrastive autoencoder. And specifically, for a given user, we generate its augmentation by masking out its domain-specific user embeddings from a randomly selected domain, and then apply the contrastive loss between the original global user representation and its augmentation. And this contrastive loss will push these two embeddings close together in the latent space, and thus we're able to further drop out some of the domain-specific features in the global user representation and result in a more general and also noisy, robust global user representation. And then in the all-for-one objective, as we have said, all the features will be transferred to the target domain for enhanced recommendation. Therefore, the final user embedding after the augmentation will consist of the following three parts. The first is the domain-specific user embeddings in the current target domain. Say, for example, the domain 2, it's the EI2. And also, it's the domain's unbiased global user embedding extracted by the catch module. And finally, it's the domain-specific user embeddings from all the other source domains. However, as we have mentioned, the domain-specific user embeddings from other domains represents their preferences or behavior patterns in various domains. Therefore, directly transferring of them may also introduce noise and cause negative transfer in the current target domain. Therefore, we further build an attention-based representation transfer unit that is the arch module in each target domain to further select possible helpful information and also filtering out possible noise from the domain-specific user representations from the source domains. Okay, in the model training, we adopted the BPR loss for training of the recommendation task, and the reconstruction and contrastive loss is used for training of the catch module. And specifically, we proposed a three-step training scheme in which we first pre-train the MF model in each individual domain to get the pre-trained domain-specific user and item embeddings. And then, based on the domain-specific user embedding, we optimize the catch module by with a self-supervised manner through the reconstruction and contrastive loss. Finally, we fixed the parameters of the catch module and also the domain-specific user embeddings that is pre-trained in the first step, and optimize the arch unit in individual domain, in the target domain, for an enhanced user embedding and also enhanced recommendation. And to evaluate the effectiveness of our method, we have collected data sets from PCG and Tencent, where over 1 million of users and their interaction histories in 5 domains are included, including their app installation and recent app usage, their article reading, and long and short video watching. And also, except for the single domain MF model, which is the base model of our proposed methods, we have also compared to a range of baselines, including the SOTA MTCDR solutions, such as MPF and Hierograph. And precision recall and NDCG are used as the evaluation metrics here. And this table summarizes all the experiment results for all the methods in the 5 domains. And we can, where the down arrow denotes there is a negative transfer compared to the performance achieved by the SMF model. And we can see that our catch arch model is able to improve performance and avoid negative transferring in all the domains, in all the 5 domains, which is significant because all the other baselines they still suffer from negative transfer in some of the domains, and they also don't have a better performance compared to our model. And finally, to evaluate the effectiveness of each proposed sub-modules, we conducted extensive ablation studies. Specifically, we gradually incorporate each proposed sub-modules into the base model, that is the SMF model, until all the features are incorporated. As shown in this table, through autoencoder or contrastive autoencoder, we're already improving performance and avoiding negative transfer in all the 5 domains, which demonstrates the importance of unbiased global user representation. And because both previous methods, such as shown here, the hero graph, and MPF, they also aim to extract global user representation, but it's directly trained on the raw data collected from all domains, and they suffer from unbalanced training data, and therefore they still suffer from negative transfer. But we are already get rid of the negative transfer through only the use of global user representation, which is unbiased, extracted by our CAT module. And we further boosted the recommendation performance by incorporating the domain-specific features through the art unit, and finally removing the attention mechanism in the art model result in negative transferring in 3 domains, which shows the necessity of attention for selecting useful information and also filtering out possible noise from the domain-specific user embeddings from all the source domains. And okay, that's all we have today. Thank you.